Recording in progress.
Alright everyone, welcome to the first talk of the 5th week of this beautiful science semester, and our speaker is Alex Rutar from University of Jyväskylä, or however it's pronounced. I do apologize. I'm very, very sorry. And he will talk us what happens when you omit some numbers, some digits in the continued fraction expansion, and the full titles on the board.
Great. Thank you so much. It's nice to see lots of familiar faces, and I guess some new faces. I really enjoyed the conference so far, and I'm very happy to start out the Fractal Geometry Week by still talking about continued fraction sets. But I guess I'm going to talk about continued fraction sets from the perspective of somebody who does fractal geometry. So, okay, let me start with a definition that we've seen, I guess, probably at least 10 times, maybe more. Okay, so if I fix a number in the open interval, which is irrational, then this number has a unique regular continued fraction expansion. So we can write x is equal to 1 over a1 plus 1 over a2 plus 1 over a3, etc., where the a sub i's are natural numbers. We've all seen this. So if x is in this form, I'm going to write x, I'm going to use this notation. a1, a2. Right. So we've seen a lot of things about continued fraction expansions and why one might be interested in these things. So from the perspective of fractal geometry, what kind of sets am I interested in? So I'm interested, this mini course is basically going to concern the following type of set. So if we look at all the numbers, the continued fraction expansion can use any digits in the natural numbers. So I'm interested in the following. So if we fix some set of digits, let's call it d. So maybe this is an infinite set of digits, so it's just some set of digits. I guess it should be non-empty, otherwise things aren't going to go so well. So we fix some set of digits, and we are interested in the following set. So what do we want? Well, we want a set of numbers, let's say in 0, 1. With the property that the continued fraction expansion has digits which only appear in the set D. And basically, this is the only thing that I'm going to talk about. So I'm just going to talk about this set. And what am I interested in saying about this set? So this is some subset of 0, 1. But if we omit some digits, if D isn't the entire digit set, this is some sort of invariant set. And it's a set with fractional dimension. So this is measure 0. So if D is not the whole set, then the Lebesgue measure is 0. Let me give this a name. Let's call this set lambda sub D equals 0. And we are interested in some fractal geometric properties. So actually, I'm going to be even more specific than this. So I guess maybe before I continue. So I guess this all makes sense. I think we've seen this at least 10 times. We've even seen this maybe a few times. But I guess the main thing I want to point out, okay, so yeah, is that the set D really can be infinite. And really, in this talk, the most interesting case will be the case that D is infinite. So if D is a finite set, somehow everything I'm going to say is not too difficult. The most interesting case occurs when D is infinite, in which case this set, lambda sub D, has quite a complicated structure. So as a fractal geometer, I guess, what's the most kind of natural question that we want to ask about a set? So we have an unknown set with measure 0. What would we like to know about it? Well, we would like to know, let's say, the dimensions of the set. So how does this set scale in space? This set. lambda sub d fill space. So to be precise, I'm going to talk about three things. I'm going to talk about the Hausdorff dimension. So this is, I guess, I think not one. I don't know if it's just like classical, but this is due to Malden and Urbanski. Throughout the year, I think it's like sometime in the late 90s. Maybe 6. And then two other notions of dimension, the upper box dimension. The same people, but in a later paper. And then I want to talk about the lower box dimension. And the results on lower box dimension are some much more recent, as due to Amon Badaji and myself from, I guess, a couple years ago now. 2025? I can't even remember. Sometime within the past few years. So we're interested in the in something. We're interested in knowing something about the structure of these sets lambda sub d. And to be precise, in this mini course, we are going to focus on these three notions of dimension. So, so the first question I want to ask: so who is familiar with all of these notions of dimension? In the sense that if I told you to come up here right now and write them, you would write. So please raise your hand if you could do that. If you could come up to the board and write these notions of dimension define these on the board right now. So I guess the vast majority of. Okay. Well, I think there's not enough people who aren't totally confident to come up here and literally write this right now. So I will this go. Okay. So I'll come back to this. In a bit. Okay. So the first thing I want to say, I guess, before I go into this more, so I'll come back to dimensions later, but I want to explain how I think about these sets, or at least how I prefer to think about these sets, lambda sub d. So again, this is something we've seen not quite as many times as the definition of regular continuous fraction. We've seen the Gauss map. Right, so the Gauss map is a map which goes from, say, the set of irrationals to the rationals. And what does it do? Well, it takes a point x, and we take the reciprocal. We take the point x, we take the reciprocal, and then we take it mod 1. So because it's an irrational, this is well defined. We start with an irrational number, we will end up with an irrational number. And the point is that these sets lambda sub d are invariant sets for the Gauss map. I mean, they're not the only ones. So they're invariant sets for gamma. Forward invariant. I mean, they're not the only forward invariant sets, but I think this is a reasonable candidate for the simplest examples of forward invariant sets for gamma. So if we draw the Gauss map, the board, again, which we've seen, well, we have at some point 1 here. We have 1 on the right here, and then 1/2, and then 1/3, and then 1/4. Sure. Well, it looks like the graph 1/x that's been squashed down. So let me draw some lines here. One branch like this, move this point a bit, and a branch like this. Hard to draw this on the board. So the Gauss map looks something like this, again, which we have seen. So there are infinitely many branches. One branch for every single digit. So for each digit, there's a single branch, the one branch for each digit, and this set's lambda sub d, so they're invariant for gamma. And how can they be understood? Well, the set's lambda sub d, so one way to think about them, if you really like dynamics, is to imagine that we just put some holes in the domain here. We emit some of these branches. So we fix our set, we fix our digit set d, and we ask, okay, well, which of these intervals corresponds to a digit not in D. So this is digit 1, this is digit 2, this is digit 3, etc., etc. We take the ones which are not in D, we delete them, and then we ask for those points whose orbit under gamma does not enter into one of these intervals. Right. But, so, I guess, if you really like dynamics, this is certainly a very natural way to look at these sets. The way that I like to look at these sets is from the perspective of iteration, which is basically the same picture, but you just like turn your head sideways, I guess. Okay, so how can we describe this set? So we have this set of points. We want to understand what is the set of points which does not hit any of these intervals. So instead of kind of iterating the Gauss map and asking which point, what are the points which avoid all of these intervals, instead we can describe such a set by iteration. Okay. So if I fix a digit, here, let's call it some digit b. So fix a digit b, let's say this interval. So this is a digit b and n.
Meeting is being recorded.
Sorry, Jesus Christ.
Sorry. No worries. So we fix a digit b and n, and we look at the restriction of the Gauss map to the corresponding interval. The interval, let's say, 1 over b to 1 over b plus 1. Yeah. So if we fix b and n, and look at the Gauss map, restricted to some interval, I guess 1 over b plus 1 over b. So the Gauss map restricted to the interval, this is a single branch, so in particular is invertible. So actually, because it's invertible, we can define as inverse. So phi sub b, let's say x, is equal to 1 over x plus b. So this is now a map which goes from the interval. I mean, a priori I've only defined the Gauss map on irrationals, but this map is of course totally fine to define an interval. This goes from the interval, which takes the unit interval and then maps it down to precisely this interval. This 1 over b plus 1 over b. And what does it mean to be in the set lambda sub d? Well, the set lambda sub d, you can kind of just check this. So one can check that lambda sub d equivalently is the maximal set, which is invariant in the following sense. That we take the union over all digits well, so first of all, it satisfies this property. And moreover, it's the maximal, let's say pointwise maximal set with this property. So let's say, right, it's pointwise. So all I've done is I just flip things around. So if you're, this is the perspective of iterated function systems, which again we saw in a few talks last week. So now instead of thinking of a picture like this, we're now thinking of a picture that looks something like the following. So what do we want here? So we have a set, we want to understand the set lambda sub d. And the set lambda sub d is essentially composed of a number of rescaled copies of itself. I mean, I guess if we think about dynamics, see if you like to think about dynamics, this makes more sense, right? And this makes sense as well. Of course, like at the first level, we've emitted a whole bunch of intervals like this. But if we started in the corresponding piece in the interval inside here, of course, we apply gamma, we're going to, if we hit one of these intervals after applying gamma, then this is also an emitted point, right? So we take kind of all the things that we've emitted at the first level, and then kind of take this entire set, rescale it down into this interval, and then look at all of the corresponding things that we've emitted corresponding to the same digits, and do this again. So this is where this kind of self-conformal structure is coming from. So I'm just saying, well, don't worry about the Gauss map at all. We can just completely understand things by looking at this picture. So what is this saying? So we start with the interval 0, 1. And then we, I guess, write the interval 0, 1 as we do the same. We draw the exact same picture. So we have 1/2, and then 1/3, and then 1/4, 1/5. And then we have all of these maps phi sub b. So we fix some digits at d, which means that we've excluded some of these. So we've excluded, let's say, this one, and we exclude this one, and we exclude this one, but we keep some of these. And for each of these intervals, the map phi sub b is the function which sends the entire interval down to this thing. So we draw the subinterval corresponding to this one, we draw the subinterval corresponding to this one, etc., and then we iterate. So we have some procedure which takes the unit interval down to each of these intervals, and then now we can apply the exact same procedure inside each interval again. Take them at the unit interval of this interval, and we do the same thing. We have the same gap pattern. So this isn't a genuinely self-similar set, so note that the set will look a bit distorted inside each of these pieces, but oh well, we will be able to handle that, not a problem. Again, like this. So we get some sort of fractal set which looks like this, right? So we started with the interval. We've subdivided the interval into some countable collection of subintervals. And then we do this again inside every single interval over and over again, and then we take some sort of intersection over all the intervals which we've constructed, and that's how you describe, that's how you get the set lambda sub d. Okay, so far so good. So hopefully 80% of people have seen this before. But I should still ask any questions. I mean, this is like, yeah, any questions about this? Please ask now, because I'm going to be talking about this like truly for the next, I guess, 270 minutes. So if you have questions now, ask them now. And if you have questions which come up like while I'm talking, please interrupt me. I know there are a lot of notes. I don't have plans to go through the entire notes, and the amount of content that I've prepared is relatively low. So please interrupt. I'm very happy to elaborate on things which I'm saying. So if there's something which is confusing for you, it's probably confusing for somebody else. So please ask me, and I will explain more about it.
Okay. For instance, if I choose d equals 1 and 3, then do I get like countermiddle thirds? Something like
Yeah, something like a middle third set. Exactly. So if you choose d to be a finite set of digits, then you only have finitely many of these intervals. Exactly. And then you take each of these finite intervals and you replace it by some finite subset of subintervals, and you iterate. Yeah. Exactly.
As 0d is also potentially infinite.
Yes, precisely. So d is potentially infinite, and d, the infinite case, yeah, is the most, I guess, the case which is the most poorly understood. I'll say that. Yeah, maybe just repeat that. Yeah. So most interesting case. Okay. That's good. So we have these sets lambda sub d, which are what we're going to view as invariant sets for some sort of some collection of maps, and we're interested in these questions. What is the Hausdorff dimension? What is the upper box dimension? What is the lower box dimension? What can we say about how the set lambda sub d kind of occupies space in a few different senses? All right. Okay. Well, I will define these things anyway, even though it's not strictly necessary. Yeah. So I guess if you're if you work in fractal geometry, it's very kind of natural. So if you just think about like the dimension of a dimension of a manifold, of course there's only like one way to define dimension. But if you work in fractal geometry, I mean everyone is very used to seeing a whole zoo of dimensions, right? There's like a lot of different things. I mean certainly Hausdorff dimension, then upper box dimension, and so why are there so many different types of dimension? Well, I guess the main reason is that the different types of dimension capture something a bit different about how a set scales in space. For very nice sets, for example manifolds, all of these things are going to coincide. But for sets which are less nice, these notions are going to give something different, and the fact that they give something different kind of tells you something about the set in addition. Okay, yeah, so certainly the most common notion of dimension is the Hausdorff dimension. I'm just going to write that down. So the Hausdorff dimension of set E, I guess it's the most natural thing to define. It's sort of the most natural notion of dimension because it's sort of it's defined using a family of measures. So the Hausdorff dimension is, I guess, the easiest way to write this is that you can write it as the supremum over S greater or equal to 0. Hopefully I don't get this backwards. So the Hausdorff S measure of E. I guess I want this to be infinite. And then what is Hausdorff S measure of E? So where Hausdorff S measure of E can be defined using covers. Well, I guess maybe I should start with Hausdorff S delta measure of E. Well, that's equal to the infimum over sums of the following sum form. Let me write it down and then I will explain. E sub I raised to the power S, where E union over E sub I. And then S measure of E. Okay, so we're trying to understand something about how does a set fill space. So Hausdorff S measure is sort of measuring the scaling properties of a set from an S-dimensional perspective. So Hausdorff S measure says, okay, adopt an S-dimensional viewpoint in RD and ask how large does a set look like from an S-dimensional viewpoint. And then the Hausdorff dimension asks, what is the best exponent from which to view the set E from an S-dimensional viewpoint? So I won't talk too much about Hausdorff dimension, but I do want to emphasize this. I guess this is the kind of the feature about Hausdorff dimension that's the most relevant right now, is that the Hausdorff S measure is defined using covers. So this condition here says that we are interested in covers. So the Hausdorff S measure is defined in terms of covers. And what are the restrictions on the types of covers which we are allowed? Well, the only restriction is this one. The dimension of the covers has to be small. I mean, we're going to take a limit as delta goes to 0, but yeah. So the only restriction is that the diameter must be small. So otherwise, the Hausdorff dimension is very flexible. So the Hausdorff dimension is defined in some sense using covers, in this sense, I guess, using covers, but the restrictions on the covers which are permitted, there are very few restrictions. So basically, you're allowed to use the best possible cover where the sets, these E sub i's can be much larger in some areas than others. So some of the E sub i's can be very large, some of the E sub i's can be very small. So, I mean, this is a very robust notion of dimension. It has a lot of good measure theoretic properties. It has a lot of good scaling properties. I mean, Hausdorff dimension, if you're in doubt about what sort of dimension you want to use, you would use Hausdorff dimension. But it is rather difficult to calculate in some cases. And also, sometimes this is measuring something too fine. And we're interested in other things. So the other two dimensions that I wrote on the board are the upper and lower box dimensions. So the upper and lower box dimensions say, well, instead of asking for covers of any size, let's make this restriction that we're going to require all of the elements in the cover to be the exact same size. So it can be phrased as the following. So given a number r in 0, 1, I'm going to write n sub r of E. This is equal to the least number of balls of radius r required to cover E. So now in this setting, instead of asking for some sort of optimization over all possible covers, we just ask for optimization over covers where all of the balls have exactly the same radius. And then we're going to do the upper box dimension. So left soup as r goes to 0. So we're interested in this covering number, and we're interested in some sort of exponential scaling rate, in the sense that the s is in the exponent here. Over. And then, of course, this limit might not exist, so we can also define the lower box dimension. Okay, so these are three notions of dimension. Any questions about this?
So can we measure that for any metric space as well?
Yeah, so any bounded metric space, this makes sense. Yeah, I guess also this makes sense in bounded metric space. Yeah, I guess, again, this is also a good time to ask questions, because I am sure that the following talks this week will also use these things. So if you haven't seen these things and you have some questions about this, please ask now, because it'll be also relevant for example, I'm sure Edward's talk, for example, and things like this. Okay. Fine. Okay, so what's going on? So let's remember. So we've fixed some set of digits, and we're looking at the sets lambda sub d, which are constructed in this way. We are most interested in the case that the set of digits is infinite. And what precisely are we interested in? Well, we're interested in these three notions of dimension. The question is, what can we say about the Hausdorff dimension of lambda d, the upper box dimension of lambda d, lower box dimension? Sorry. And when I say what can we say about these things, well, the best thing would be to be able to say what these numbers are in terms of d. So you give me digits at d, and then I would like to be able to explain, or like to maybe some formula, maybe one might hope for a formula, maybe one might hope for something slightly worse than that. Anyway, so you give me digits at d, and I can we understand? And I guess the kind of a quite interesting question, other than kind of determining exactly what these values are, is can we understand when these numbers coincide? Can we understand when they coincide? So even if we get some sort of formula which looks potentially a bit complicated in terms of the digit set, we would still like to be able to say something about the regularity of the set. Because what happens if the Hausdorff dimension and the upper box dimension coincide? Well, that says that, you know, all this extra flexibility you gained by having covers of many different sizes, well, that was totally useless. You might as well have just taken covers of all the same size. And actually, all the extra flexibility you got in scale, well, that was also totally useless. You could have taken any scale you want, and it would have worked.
There's a question from one of our audience online, which is how much of all your discussion will extend where D is now a subset of allowed or forbidden words?
That's a good question. Yeah, so certainly that's been done for these two. For Hausdorff dimension and upper box dimension, there are papers by Mariusz Urbanski and collaborators where they, I think Mariusz Urbanski and Malden and things like this, where they talk about like graph-directed systems on, yeah, a more complicated version of this. So in that case, certainly yes. For lower box dimension, at the moment, no. I have not thought about this at all. This is probably something interesting to think about. Okay, hopefully that answers the question. All right.
Is there some pathological reason why lower box dimension would not have similar results, or that, you know?
Yeah, exactly. So that's kind of what this mini course is about. This is kind of why I'm excited to talk about this. Is it turns out that like Hausdorff dimension, I mean, if you've seen this before, so I'm sure a lot of you actually like literally seen this before. And it turns out that there's like Hausdorff dimension and upper box dimension, like things are quite nice. There's kind of a nice concrete formula for the Hausdorff dimension, upper box dimension. But for the lower box dimension, it turns out that there isn't. There's actually no nice formula for the lower box dimension in terms of, well, you can give a formula in terms of D, but it isn't so nice. It's rather hard to unpack. Yeah, and there are good reasons. I think there are some good geometric reasons for why this happens. And then the goal of this mini course is actually to explain, like, why is the lower box dimension so much more pathological, basically. So I mean, ultimately the goal is sort of to say something meaningful about the structure of the set lambda D. And once we sort of really understand what the set lambda D looks like, we'll just be able to read these things off for free, or read off some variant of these things for free. That's kind of the goal. All right. What do I want to keep? I keep this. so the first thing I want to mention is that there's nothing particularly special about the fact that we start with this set of continued fractions. So for the remainder of the talk, I'm going to work in a slightly more general setting, and the slightly more general setting is the following. Okay, so yeah, so in this case, what do we have? So we have some countable index set D. We have a whole bunch of maps which are taking some compact interval or some compact set and mapping it into itself. These maps are, well, basically contracting. I mean, yeah, if b equals 1, this thing has a derivative of 1 at one point. But if you iterate, if you like look at like some compositions of these things, they're contracting maps. So here's a somewhat more general setting in which we can discuss this. So what am I going to do is I'm going to fix, so we're going to work in RD. I promise that there is no d-dimensional geometry going to show up. Everything works in RD just by writing d everywhere that's appropriate. I fix a compact set X. RD is compact. And then what do I have? Well, kind of in analogy to these maps phi sub b, I have some collection of maps. Let's call them f sub I. I will try to always use f sub I for these things. So we have some collection of maps I, where I is countable. By countable, I mean finite or countably infinite, with the most interesting case being when it's countably infinite, where each f sub I is a map which goes from X to itself, and it has the property that it is a contracting map, in the sense that if we look at the distance, let's say the Euclidean distance between f sub I of X minus f sub I of Y, this is bounded above by some, call it some constant xi, times the distance between X and Y, where xi is strictly less than 1 is independent of I. Of course, in the case of infinite, this is actually important. So basically, I'm very explicitly kind of allowing that, so these things have to be proper contractions, and I'm very explicitly disallowing the case where the contraction ratios kind of get close to 1. So they have to always be uniformly far away from 1. Right. So, of course, so here the setting, like I is just D, X is just the unit interval, then f sub I is just the map which takes X and maps it to 1 over X plus B. Fine. So for better or for worse, of course, it would be great to be able to like say things in this generality. This is totally impossible, essentially. So we need more assumptions. So this is basically okay. So under only these assumptions, we have some initial set. We have some collection of maps which map the set into itself. So under these assumptions, there exists a maximal invariant lambda is equal to the union over I and I sub I of lambda. So the existence of the set lambda isn't special. This only depends on the fact that we're contracting, and even if you remove the contracting assumption, it still usually works. Although you have to be a tiny bit more careful. And we're interested in lambda, in this set lambda. Of course, okay, so the catch, if you've worked with iterated functions systems at all, there are the usual caveats. Actually, I might mention that, okay, so if you've seen this in the case when this is finite, then actually this statement becomes, there exists a unique compact, non-empty compact. I'll just say this. So if I is finite, there exists a unique non-empty compact set lambda satisfying this equation. So this is perhaps, a lot of you have seen this. So the reason why there exists a unique non-empty compact set lambda is because this operator, which takes a compact set and maps it to a finite union of images itself, it turns out this is a contraction mapping on the metric space of compact subsets of X equipped with the Hausdorff metric, and then by the fixed point theorem, there exists a unique compact set. But in the infinite case, this is no longer true. So this set is no longer compact. Actually, this is a funny open question. I'm not going to talk about this at all, but if you're interested in this, you could. So the question is the set lambda a Borel set? This is actually not known in the infinite case, surprisingly. Yeah, it's a bit horrifying. So it's always an analytic set. So we're not like totally screwed, right? So is it always an analytic set? Because you can kind of conceive of it as a continuous image of the sequence space, right? So if we start with the sequence space, like the set of all infinite sequences, and we take a point, we can map sequence space into lambda, where we just look at kind of repeated compositions. So it's a continuous image of this space, which is a polar space. So it's a continuous image of some nice space. But I think it's open. It's an open question in this generality. I want to emphasize in this generality if this is a Borel set. Okay. Anyway, but of course, like if you're talking about iterative function systems, there's basically no hope that we can say something meaningful at this level of generality. So we basically have to make two kind of caveats, or two kind of extra restrictions. So the first restriction is that we have to assume that the maps are somewhat nice. So the f sub I must be somewhat nice. I mean, what somewhat nice means really depends on your setting. It depends on how hard you're willing to work. And the second caveat is that the f sub i's, the intervals f sub I of x, must not overlap too much. Yeah, so if you violate one, you can basically do anything you want. This was Simon Baker's talk last week. If you just assume these things at the level of like biological generality, I mean, they have this like whole kind of collection of counter sets, which could be the attractor. So if we just assume these things, if we just assume Lipschitz contracts written by Lipschitz, we're totally screwed. So we better assume they're going to sound nice. And here, somewhat nice means essentially self-similar. What self-similar means is that the image, that f sub I of lambda basically looks like lambda. Like a rescale copy. Lambda. That's what this assumption means. And okay, so what about the second assumption? So I'm just, again, going to briefly talk about this. I'm not going to dwell on this too much. When we looked at the Gauss map example, or when we looked at this like continued fraction, this inverse branches of the Gauss map, we had this very particular property that all of the images of the initial set, well, they only overlap a tiny bit, right? They only overlap at most at the endpoints, and sometimes not even at the endpoints. So I'm going to make some similar assumption of this flavor, some assumption which kind of covers two. Yeah. So two, I'm going to call this the bounded neighborhood condition. Let me just try to write this down precisely. Oh well, so much for having notes. I can't find it, so I'm going to go from memory. Okay, so the bounded neighborhood condition basically says this, that the f sub I of x must not overlap too much. So what is the bounded neighborhood saying? So the bounded neighborhood condition says, if we fix a ball b of x r, and we look at this collection of words, let's say, okay, so let me introduce some more notation. Okay, so I'm going to introduce some notation which I'm going to use. Okay, so yeah, so there's some sort of like natural coding by this infinite space IN. So if one is interested in these images, okay, so we have this picture. I'm just always going to draw this picture. I'm going to draw this picture where we have some intervals and we have some intervals and like this. Right. So at the first level, each of these intervals corresponds to some digit. This corresponds to some index I and I. This is like some image f sub I of the original interval. And then when I iterate, of course we get another copy of the same interval inside itself, inside all of it. And then this is obtained by taking image f sub I, and then we can get here by taking image f sub j. So if we talk about finite words, so I star is equal to the finite words on I. So by that I mean like things of the form I1, IN, where I sub j in I. There's a correspondence between elements of I star and these sets. So these correspond to elements in I star. So if I fix, I'm going to try, in the notes I've written this in this like typewriter font. So if I fix this like word in I star, I will write the following. I'll write f sub I. This is note the composition. F sub I1, f sub IN. And then I also use this notation rho. So rho of I is the contraction ratio. Which you can think of as like the width of the interval. Okay, Yeah, so you can check the notes for the more precise definition. I'll define these things slightly more precisely later. You can also look at the notes for more precise definitions. But basically, rho of I is kind of is measuring like how much is this map contracting? We have some image of the interval, and we want to ask like how large is that interval? Because we're interested in covers or we're interested in the size of the set, and this is the meaningful quantity. Okay, so what does the bounded neighborhood condition say? So the bounded neighborhood condition says that the images f sub I of x do not overlap too much. And here's what I think is a natural way to write down this condition. So we have a ball B of xr, and we want to say that these images don't overlap too much. So in particular, we can say something like, not too many of these images hit a given ball. Right? But there's a bit of a catch, there's a slight catch, and the slight catch is that of course this is an infinite set. Right? And if I put a big ball here, near the tail, of course infinitely many things are going to hit this ball. So we can't literally say that there's only a finite number of images f sub I would hit this ball. If this were a finite index set, we could say something like this, or like there's some reasonable word in this. So I need to make a slight restriction. So the bounded neighborhood condition says there exists a constant m greater than 0, such that the following holds. For all, so what do I want? So I want for all sets f I star. Okay, yeah, so another thing is if I fix a small ball down here and I look at like, let's say of course I could look at what things hit this ball. Well, this hits this ball, and this hits this ball, and this hits this ball. So there's kind of like a nested sequence of things which hits this balls, which overlap with this ball. So this is also something I want to exclude. So that's what I want to exclude down. So for all f contained in I star, which is mutually incomparable, so what do I mean by that? So by mutually incomparable, I mean that there's no I, comma j, which are prefixes. So there are no words I and j in f, such as I is a prefix of j. So basically, we never have the situation where we look at this thing, then we look at this thing. So there's just some sort of condition that says like, okay, choose a bunch of intervals which are disjoint. Disjoint in the symbolic sense. So if we choose a whole bunch of intervals which are disjoint in a symbolic sense, and then we count how many of them hit this interval, so that we count the number of I in f, such that, well, what happens if this interval intersect with f sub I of x is not empty? But then what was the second caveat I said? The second caveat I said was that if you put the ball at the bottom left corner here where all the things are accumulating, of course, this is still going to be infinite. So I'm also going to require that this contraction ratio is large. So rho of I is strictly bigger than r. So this set, so the things which hit this ball and which have large contraction ratio with the requirement that there's some sort of symbolic disjointness, the cardinality of this is at most half. Okay, so this is what the bounded neighborhood condition says. So, and there's a few extra technical caveats as to why you have to define it like this, but this says essentially that the f sub I of x's do not overlap too much, and this is just a really convenient technical way to formulate this. I think this is maybe the most convenient, in my opinion, the most convenient technical way to formulate this. Probably, you have seen other conditions that I'm really not going to talk about, but we've seen conditions like open set condition, which say things like the f sub I of x intersect f sub j of the interior of x not empty, empty, for I not equal to j. There are conditions like this. There are conditions like this which kind of require that, which state that, like this is really clearly like a not overlap too much condition, but it turns out that this is kind of totally sufficient. So this is sufficient in the generality. This is sufficient.
Excuse me. This lambda star. What was? I could not read.
Sorry, I star. It's I. So I star is the set of all finite words.
Fine. Oh,
Finite words on
I is okay.
Yeah, exactly. Yeah. Precisely.
What's the intent of having rho greater than r?
Right?
What's the intent of supposing rho of I to be greater than r?
Yeah, it's exactly this. Because if I take this ball B of x r, and so because we have a countable index set, if I take this ball B of x r and I put it at the corner here, it's going to hit infinitely many of these like tiny intervals. So I just want to like omit that case. I want to say don't worry about tiny intervals. And this is like the simplest possible way to do that, I guess.
Like open set condition if we have just finitely.
So open set condition always implies in the finite type case this is basically the same as open set condition. I mean it's literally equivalent. Yeah. If the index set is finite, and the maps are similarities and all the extra caveats, this is literally the open set condition. You can prove that.
I'm sorry. So our phi sub b function system is a self-similar one or not?
It's not self-similar, it's self-conformal.
So then I'm confused to why we are considering about the self-similar.
Oh, I'll explain it in a moment. That's the next thing I'm going to say, so don't worry.
R here, so the ball of radial BXR is an anti then where I is bigger than not. Is there any restriction on R? Can it not get too small?
So for all R.
For all R, okay.
Yeah, so there exists an m greater than arrow such that for all mutually comparable f, for all x, for all r. So everything is for all, so the for all quantifier for everything. Precisely. Yeah. There, to make you happy. Okay, let me explain a bit more. Okay, yeah, so, okay, any more questions about this? Yeah, so this is, yeah. Okay. I erase this.
Is that actually anything on the point if you assume that this decays with R, let's say in R?
Yeah, exactly. So one could replace this with a condition that says, yeah, this decays sufficiently fast in R, probably things are fine. But
Or not decay, so maybe it's R.
sorry, that doesn't grow too fast in R. Exactly. Yeah. So if you assume that this thing like grows like sub-exponentially as a function of 1 over R, that's probably sufficient. Although I haven't checked, so please. Yeah. This is one reason why I like this condition a lot, because somehow it becomes very clear how to relax this condition slightly to get a larger class of sets. And actually, in the finite case, if you relax this to like a condition like sub-exponential and 1 over R, it's actually already extraordinarily general. In fact, conjecturally, for all systems with dimension less than ambient dimension. But that's totally a conjecture. Okay. Yeah, so you brought up a really good point, which is that, okay, so the maps, so what do I mean? Okay, maybe let me define this precisely. So what do I mean by a self-similar map? So by a self-similar map, I mean one which distorts distances exactly by this constant psi. So for each map, okay, I just erased it. So the Lipschitz contraction condition said that f sub I of x minus f sub I of y. Well, this was bounded above by this contraction ratio, rho of I times the distance between x and y. And we say that f sub I is self-similar. It's a similarity map if this inequality holds with an exact equality. In other words, we contract exactly by this quantity rho of I. So in RD, this is precisely the maps of the form f sub I of x is equal to rho of I times some orthogonal matrix times x plus t sub I. Basically, you do some sort of like rigid transformation, and then you scale down a tiny bit by this vector. But of course, these maps are not literally similarities. So note, phi sub b's are not similarity maps. But at least for the purposes of this course, the plan is kind of the following. So for the rest of today and tomorrow, maybe half of tomorrow. So basically the moral of the story is that handling the general conformal case is sort of more technical without any new kind of properties. So the plan is essentially to discuss the self-similar case, even though this is cheating because this is not a self-similar set. So the plan is one, to discuss the self-similar case. So the reason why I want to discuss the self-similar case is just because it kind of like erases all of these extra technical details, and we can really focus on what we can say about the set. What sort of like new things are going on in this infinite system, in this infinite case, and then I will later explain how to remove these, how to generalize in less detail. To generalize to a self-conformal case. So basically the idea is that if you look at these maps and you look at a really large composition, they essentially look like similarities. They're close enough, they're similarity up to some constant error term, and you can kind of just like handle the general self-conformal case in a morally similar way to the similar case with a decent number of extra technical work. So that's why I wrote self-similar, and that's kind of what we're going to talk about now for the rest of the time. For the rest of today, at least. And then probably tomorrow, too. Probably Wednesday, too. Okay. Right. So let's just kind of summarize the situation. So we're interested in these sets lambdas of D. So we fix some digit set and we look at those continued fractions which with expansion, those points with continued fraction expansion consisting only of digits in D. We inverted the branches of the Gauss map and we thought about this set as an attractor for some sort of iterated function system. So we have some countable set of maps and the set lambdas of D looks like a bunch of rescaled copies of itself under the maps phi sub B. But of course, we don't need to think specifically about this condition. We can think, generally speaking, about an arbitrary iterated function system, with the caveat that the iterated function system must be somewhat nice, in the sense that the maps must be vaguely self-similar. I will say self-conformal. I will explain what that means a bit later. So generally speaking, self-similar, and the images must not overlap too much, but these two conditions are both going to be satisfied by this thing. So in particular, everything that I say eventually is going to be satisfied by that specific system. Okay. And we're interested in Hausdorff dimension, lower box dimension, and upper box dimension of these sets. All right. Okay. So the Hausdorff method is essentially the easiest to handle. So whenever you have a set, so in order to understand Hausdorff dimension, we would like to say something about optimal covers. Or so we'd like to say something about covers. We want to say something about covers. So covers of lambda. But we have a natural family of covers. We have a natural family of covers which comes from the iteration relationship. Right. So we started with maybe I'll draw a 2D picture instead of drawing the 1D picture. No longer corresponding to this. Now it is corresponding to the general setting. Right. So I start with my set X, and then I look at the images of X. Right. I have like my images. So these are my images f sub I of x. And then inside each of these, again, I can take any one of these intervals and I can replace it again with some new intervals like this. Like the intervals look kind of the same. So if I look at the balls, or I look at these sets, so the sets f sub I, so I is now a finite word that says f sub I of x provide a natural cover. Natural covers for x. So what do I mean? For lambda. So what I mean literally, lambda is contained in the union over all words of length n, f sub I of x. Right. So we have some sort of natural cover for the set lambda, which we obtain by looking at iterations at level n. So the Hausdorff dimension, I guess, the kind of, if you're in this case where this small scale copies essentially look like the original set, the natural guess is that these covers are optimal. It's the natural guess is that these covers are optimal. So, well, certainly one direction immediately works, right? So the fact that we can use these covers to get an upper bound on the dimension of lambda, well, this is not too difficult to show. Okay. So let's just use these covers and let's see what kind of upper bound do we get. Okay. So in order to say something about Hausdorff dimension, let's understand the S cost of this. So the Hausdorff S measure of lambda, well, that's bounded above by the Hausdorff S measure of So the Hausdorff S measure is defined in terms of infimum over all possible covers. In particular, we can take literally these things as covers, right? So we can, this is bounded above by the sum over I in In, the diameter of this, I of x, raised to the power s. So because we're contracting, if we raise n to be large, I mean there's an implicit delta. There's an implicit delta inside here, which we're taking a limit of, but if you make n to be sufficiently large, all of these things are going to have diameter of most delta, so don't worry about it. But what is this, the diameter of f sub I? Well, we're assuming that we're in the self-similar case. So if it's a similarity map, the similarity map literally preserves distances. So the diameter of f sub I, well, this is equal to the sum over I in In, rho of I raised to the power s, well, up to some constant. Because of course this is the diameter of some image of x, x is a compact set, this is like rho of I times some constant, rho of I times diameter of individuals of x. But there's some fixed constant. But now that we're in the fact that these are similarities, this function rho is multiplicative. Because if you compose two similarity maps together, how does the similarity ratio compose? Well, it composes by multiplication. So this is equal to the sum over I in I. So we only look at the sum of level 1 intervals, rho of I raised to the power s, and then we raise this thing just to the power n, right? Because I can write these things as a product, and then I can expand on the product just by multiplying with the sum. Right. So we're interested in, so this kind of says, okay, so in order to understand Hausdorff dimension, we're interested in when is this number infinite, or for what values of s does this cross from being infinite to finite? And we can just look at the sum. So when does this number go between infinite and finite? Well, if the sum on the inside is bigger than 1, this will be infinite. And if the sum on the inside is less than or equal to 1, this will be finite. So that gives us our natural guess. So that gives us the natural guess for what the dimension should be. I'm going to start erasing this. So now we can forget about continued fractions, and we'll come back to it later. Okay. So I'm going to define this thing which is called the pressure function. So we're going to define a pressure function. Define the pressure. So the pressure function is so it's something which depends on the IFS, and it depends on some parameter t. And what does it do? Well, it's basically going to be just this sum, and then it turns out that it's kind of natural to take a logarithm. So we're going to take a logarithm. But of course, now the kind of important caveat here is that I is an infinite index set. So if you're thinking about this from the self-similar perspective, you're like, well, this is easy. Now just take s to be the number for which this is 1. But in the infinite case, this no longer exists. Okay, so kind of in this view, so we would like that p of s is equal to 0, which is the same as the sum being 1. But this isn't always possible. Always possible. So essentially what can happen? So let me draw a graph of this function. So this function, okay, because all of these rho of i's are not just less than 1, these are strictly less than psi. So there's some like uniform contraction ratio over all of these. Right? So because there's a uniform contraction ratio, p of t is a strictly decreasing function. So p of t, so I guess let me look again, because so the first fact is that p of t could be finite. Okay, so it could be infinite. So if you take t to be equal to 0, then this is just a sum over some infinite set. Of course, this is dead. So if I is infinite, then p of 0 is equal to plus infinity. So this function doesn't necessarily take finite values, but the function looks something like this. So for some time, it's equal to plus infinity. So it's literally plus infinity for some time, and then there's a number here, where it starts to become finite. So either it becomes finite either at this endpoint or maybe it's an open endpoint. Let's say it becomes finite somewhere. So the function p of t becomes finite at some value. And then once it becomes finite, it has to be strictly decreasing because all of these are strict contractions. So it has and not just strict decreasing, there's like a uniform upper bound on the slope. So it has to be strictly decreasing with some rate. So eventually it goes like this. So this is the picture when life is really good, because now the pressure has a 0. So in particular, if it's a finite index set, of course it's already finite at 0, in which case certainly we have a 0. But the thing is, it's totally reasonable that this picture could happen. So there's nothing where we start, where we're at plus infinity for a while, and then we just immediately jump to being negative. So we never hit 0. So we don't have a 0 because of this phenomenon, because we have plus infinity, and the moment we're finite, we're already negative, and then there's no chance. So we can't necessarily find a 0. But this point here, this value here, the value h, it's called the value h, this is equal to the infimum over t, such that p of t is less than 0. This is still a natural guess. This is still a natural guess for the dimension, is the natural guess. So certainly, what did we prove here? Well, if number t is strictly bigger than h, then the pressure is negative. The pressure being negative means that this sum is strictly less than 1, and in particular raised to the power n, this converges to something finite. So, in particular, we already saw that the Hausdorff dimension of lambda is at most h. Okay, so maybe then the next thing to mention is, what happens if this literally has a 0? So what if there exists an S so if there's literally a 0, then we're in pretty good shape, we're in better shape. Because, okay, so in order to get an upper bound on dimension, we have to prove the existence of some cover. But in order to give a lower bound, we have to say something about all covers. In order to say something about all covers, the easiest way is to put a measure on the set. And you use something like mass distribution principle. So I'm going to just kind of briefly sketch this. So I'm not going to dwell on this too much, but I'll do briefly sketch this. So what happens if there exists an S that is literally 0? Well, now this equation, so this thing being equal to 1, equal 1. So then we can define some probability measure on this infinite space. Some probability vector, I guess a probability measure on the infinite space, which is infinite product measure. Of, let's say, this row of i's, S. So the fact that it defines an infinite product measure is really using this fact that there's a 0. Because we use the 0 when we define the measure of a single I to be exactly this number, row of I raised to the power S. And then the fact that it's a probability measure works out because the sum is equal to 0. So we define some sort of infinite product measure, and then we take some sort of push forward. So we take an image. So this is a measure which lives on this sequence space, but the sequence space kind of corresponds to that lambda is a reasonable way. So to get a lower bound, and we look at some push forward of this measure on lambda, where pi is some projection map. Is the map which takes some sequence I1, I2, I3, and what does it send it to? Well, it sends it to the composition f sub I1 composed f sub In, the limit of some starting point x0. Okay, so we have some natural symbolic space. We put a measure on the symbolic space, then we use it to construct a measure on the set itself, and then we use this measure to get a lower bound. And then we can check that the corresponding measure, let's call it equal to mu, has some sort of like nice property that the measure of a ball is up to a constant r to the s, and this in particular implies, and then it's mu is supported on lambda, and then this implies by something called the mass distribution principle, basically like it's written down in the notes. This implies that the Hausdorff dimension of lambda is what it says. Okay, anyway, so I'm belaboring the point a bit, and I don't want to talk about this too much, but essentially, if there was a 0, what can we do is we can construct a measure which lives on the set lambda, which has this very particular property, which is that the measure has kind of really nice uniform distribution on the set itself. In the sense that the measure of any ball, well, this scales like r to the s. And it turns out, just by like a one-line argument, that if you have a measure which looks like this, then the Hausdorff dimension has to be at least s. So this always gives you a lower bound for Hausdorff dimension. So the catch here, of course, is that we literally have to have a 0. Otherwise, we can't construct this measure. And it's a general fact that this measure, like a measure which has this property exists if and only if the pressure has a 0. So this is actually kind of optimal. So we can't do this in general. But if we just want a lower bound on dimension, it turns out that this is really not a problem. That we can we can kind of use this case. We can use the case where the pressure has a 0 just to give a bound on the dimension in the general case. Let me briefly write that down. Okay, maybe let me write this down as the first kind of theorem. I'll write this down carefully. So theorem. So we have an IFS f sub I of similarity maps. The pressure function is P of T. The attractor is lambda. Then the Hausdorff dimension, and also satisfying the assumption. So satisfying this assumption that the images of that f sub I of x's, these images don't overlap too much, and the fact that these are similarity maps. And the Hausdorff dimension of lambda is exactly this number h. And this is due to Molden and Obransky in their 96 paper. Actually, probably this is even earlier. I'm sure this is earlier. I mean, in their case, they're already doing the self-conformal setting, and in the self-similar setting, I'm sure this is known before. Okay. So the proof is very simple. So we already saw that the Hausdorff dimension is a less than h as we saw this. So in order to get a lower bound, so what's the situation in which we're sure that we're going to have a 0? Well, this is a finite index, and we're certainly going to have a 0. Because the value at 0 is greater than or equal to 1, and this is a strictly decreasing function, so if it's finite, we're definitely going to have a 0. So we can get an approximation from the other end by considering finite subsystems. Okay, so for the other direction, use finite subsystems. For the lower bound, finite subsystems. Okay, so if we fix some number, let's say we let t be some number strictly less than h, well, the pressure function at t, so by assumption, the pressure function at t is strictly bigger than 0. I mean, it might be plus infinity, but no problem, right? So because the pressure function was defined literally in terms of this sum, right? The pressure function was defined as a sum over some infinite instead of I at I, rho of I raised to the power t. So this implies that this number is strictly bigger than 1. But this is a sum over a potentially infinite thing, but it's a sum which exceeds 1. So in particular, this implies there exists a finite set, f contained in I, such that the sum over I in f rho of I raised to the power t is still strictly bigger than 1. Right? I mean, this is just using the properties of the fact that this is a sum, right? Like it's a sum over some infinite set that's bigger than 1, so some sum is bigger than 1, maybe infinite, who cares? Doesn't matter. We can find some subset, some finite set of indices, such that at least we exceed 1, because all the things are positive. Well, then now apply. So now we've gone from an infinite system to a finite system. So now we genuinely have this. So now this finite system has some point, which has a 0. The attractor of the finite system is a subset of the attractor of the infinite system. And because this sum is at least 1, let me write this down. I don't want to walk over that way. Let me just write that here. Right? So since this sum is at least 1, so since, let's call P sub f is the pressure corresponding to the finite subsystem. So since the pressure at the finite at t is still strictly bigger than 0, and since f is finite, this implies that the Hausdorff dimension of the attractor of this finite subsystem is greater or equal to t, which is the lower bound that we want. We found some subset of lambda with dimension which is at least t, and this was our goal. T less than h was arbitrary. So this is how you can prove it in the general case. So kind of, there's basically only one extra observation required in the general case, which is that you start with an infinite sum and you approximate the infinite sum from within by a finite sum. That's it. Otherwise, the infinite case is the same. So if you're not worried in properties like this, if you're not worried about the existence of nice measures, you're only interested in dimension, then this fact is quite easy to prove. Okay? Any questions about this? So this is Hausdorff dimension. So what's the moral of the story? So the moral of the story is, right, we have some iterated function system, potentially coming from this. The iterated function system comes with a natural family of covers. Right, comes with a natural family of covers obtained by looking at all of the images or all of the level n images of the initial interval. This natural family of covers gives rise to a natural guess for what the dimension should be, where we kind of forget about the fact that we have full flexibility, and we only look at the covers that are coming from here. And this natural family of covers gives us a guess, and it turns out that this guess, which comes from the natural family of covers, assuming that there is some sort of disjointness condition, by this argument, this is exactly the number. So the Hausdorff dimension, so in order to understand the Hausdorff dimension, we just need to look at kind of how much are these maps contracting. And we don't care about how the maps are arranged in space, other than the fact that they aren't overlapping too much. Okay, so that's the story of Hausdorff dimension. And in the last 10 minutes, I'm going to start, I won't kind of continue with too much more material, but I will explain. Let's give an overview of what's happening for the box dimension. All right. Okay. So any questions about Hausdorff dimension? Sorry, before I continue. Does that make sense? So the Hausdorff dimension is not really going to return. I mean, the Hausdorff dimension is going to be kind of implicitly sitting in the background of everything. But now we're going to focus on the upper box dimension for the rest of the time. Okay. Upper and lower box dimension. So now the question is, what about let's recall in the definition of the upper and lower box dimension that now we no longer have this full flexibility to choose covers of any diameter we want. Right? We can only choose covers which have a fixed diameter. And if we look at the types of covers that are coming out of this bound, we got this bound. What kind of covers did we use? Well, we used covers consistent of these intervals, but there are infinitely many maps. So these intervals have size which are decaying potentially very, very quickly. Right. So the kind of, I guess I should say that the covers for the Hausdorff dimension are very non-uniform. In the sense that we can't just use the same covers in order to understand box dimension. And actually, here's like a really, really simple way. Here's a really simple way to kind of quantify how non-uniform these covers are. So for each map f sub I, so for each I in I, so these maps are contraction maps. There exists some x sub I such that f of x sub I is this. So each map I has some fixed point. Let's call it xi. And we can define this that f is just a set of all fixed points. So in this picture, what is f morally? I mean, not literally, but approximately it's like, let's just take only the left endpoint from each of these intervals. So we kind of forget about the fact that this is some really nice set, some really, really nice big, some set, and let's just take the endpoint from, let's just take 1 point from every single interval, and only at the level one of this construction. That's the set f, right? So of course f is itself a subset of lambda. It's a very small subset of lambda, but it's some subset of lambda. But it's an infinite set because I is an infinite index set, and this set can be large. So in particular, let's consider the special case when we have the Gauss map. So let's say the Gauss map, and for the continued fraction sets. So in the continued fraction setting, what is the set f? Well, if D is the set of all naturals, then basically F, I'm going to put this in quotes because it's not literally here, but basically is the set 1 over B. Okay, so maybe this is always true, so I don't need to have it too. So in the continued fraction case, the set F is precisely the set of all reciprocals. I mean, this is how we define this is how, right, we have the interval 0 to 1/2, and then to 1/3, etc. And this is like the set of all left points, left endpoints, like 1/2 and then 1/3 and 1/4, right? So if D is everything, so in particular, so if D is equal to n, then the upper box dimension, or even the lower box dimension, the box dimension of this set exists, and it's actually equal to 1/2. So even though it's a countable set, if we're interested in upper and lower box dimension, if we're just interested in covers at a fixed scale, this countable set is already providing an obstruction for dimension. But in this case, okay, so maybe you say, okay, well, not a problem. Surely the Hausdorff dimension is at least big, but we can always make the Hausdorff dimension smaller. Okay, I mean, for the exponent 1/2 is not wrong, but yeah. So the point is that the Hausdorff dimension can become very small, because if we delete maps, let's suppose like we start deleting maps from the system, then the Hausdorff dimension could become smaller, but this property of the set F, the upper box dimension or the box dimension of the set F, only depends on the tail. So somehow the dimension of the set F and the Hausdorff dimension of the set are a bit decoupled. I mean, this isn't literally true in the sense that the Hausdorff dimension is still seeing something about the tail, but heuristically speaking, the upper box dimension, heuristically speaking, we can change the Hausdorff dimension of F, the Hausdorff dimension of lambda in such a way that we sort of don't modify the box dimension of F. So potentially this is a major obstruction. So in particular, so what do we know? So the upper box dimension of lambda, well, it's at least, well, of course it's at least the Hausdorff dimension, because there are more restrictions on the covers. And it's also at least this number. It's at least the upper box dimension. Okay, and this can be bigger. Plus the upper box dimension of F can be bigger. Okay. So this seems like a really trivial kind of obstruction, right? I mean, we why are we interested in a notion of fractal dimension that's so unstable that the moment we add like some countable set of points, that the dimension immediately becomes bigger? So I claim that this is not a trivial obstruction. Let me kind of briefly explain why. Okay, so 2 observations. So the observation 1 is that actually this set F is kind of, or like a variant of the set F is a much bigger issue, right? Because the set F appears at the first level, but it's a self-similar set. So where does F appear again? Well, F appears again inside here. So we again have a copy of F sub I of F inside here. So if you kind of iterate this obstruction, we actually obtain kind of this kind of tree of copies of obstructions. So we have the set F that kind of accumulates at the tail, and then we have exactly a copy of this obtaining inside every single interval. And then we iterate again, and this is inside every single interval. So actually, we can iterate to obtain kind of a much larger obstruction. And then the second property is that kind of because of this iteration property, the fact that our set contains lots of small copies of itself, that this is also the case that in fact this number is equal to something called the packing dimension. So the upper box dimension of lambda is in fact equal to the packing dimension of lambda, where you can define packing dimension in a way which kind of justifies the fact that it's called the packing dimension, but we can also define it as sort of like a countably stabilized upper box dimension. This is the infimum over, I guess, how do I define this correctly? I want something involving upper box dimension dimension E sub I, where lambda is contained in the union over some countable union of the E sub I And I guess I want some sort of image. So one way to obtain packing dimension is to take upper box dimension and countably stabilize it by saying like, okay, well, we allow ourselves to decompose our set lambda into countably many pieces, and then we take the infimum over upper box dimension of all the pieces. So in particular, because this is countably stabilized, the set F is literally invisible. But yeah. The set F is literally invisible, but these kind of iterated obstruction is actually very, very large. Yeah.
There's another question from online listeners, and I'm sorry, it's like from 7 minutes ago, so it's sorry. The question is how you compute Hausdorff dimension if given your alphabet D. Do you just solve the sum of those row I to power t equal 1?
So how do you compute Hausdorff dimension if you know the alphabet D?
Yeah.
Yeah, exactly. Yeah, I mean, that's the best way to do it.
Yeah.
But if you choose the set D in some very pathological way, I mean, you're going to have to work as hard as your pathological choice of D. But yes, in principle, you just solve this sum.
That is supreme law, right?
Sorry? Sorry, yeah. There's a super dim EI, yeah. I kind of ran out of space. Right, so I want the largest of the upper box dimensions of the pieces, and I want to take the infimum over all possible covers. Yeah, thanks. Okay, so the point is that this obstruction, which looks really silly, which is this kind of countable set, well, first of all, it's much bigger because we can iterate. And second of all, because it's so much bigger, because we can iterate, it actually turns out that the upper box dimension and the packing dimension are the same. That even if we countably stabilize upper box dimension, we haven't gained anything. That the number is still the same. So I'm not going to talk about packing dimension, I'm only going to talk about upper box dimension, but hopefully this convinces you that something like slightly non-trivial is going on. Okay. So let me just advertise what I'm going to talk about next time without just saying more. Okay, so goal next time. Well, the first thing that we're going to do is we're actually going to prove this is actually the case, that this is the upper box dimension. So we will prove in other words, even though you can iterate to obtain a larger obstruction, this never kind of makes the dimension any bigger. So kind of the intuition that we will see is that iteration can make this number kind of, these like iterated things can become bigger, but they can't become more than h dimensional bigger. So they could be larger than f, but they couldn't be larger than h. So in particular, it'll still be the case that either one of these two will win. So either we started with something which was so big that it's already an obstruction, or we iterate it and it doesn't become too much bigger, like it doesn't become much larger. Okay, so we will prove this. But I guess the more general kind of picture is, we would like to say something about lower box dimension. So it turns out, so for lower box dimension, it turns out that there is no similar formula. So when I say no formula in terms of what numbers? In terms of h, lower box dimension of f, upper box dimension of f. So even though we have such a nice formula for the upper box dimension, which is we can just write down just like this, for the lower box dimension this is no longer the case. So the goals are essentially the following. So the first goal is to understand what is going on. But I guess it's a bit too general. So it turns out that instead of asking for the upper box, instead of trying to understand the lower box dimension, it's more meaningful to ask a harder question, and we'll be able to say something. So actually, we will study kind of these covering asymptotics. We will study the function which takes R and maps it to the covering number of R of the set F at CLR. Sorry, lambda in terms of H and the function in terms of the set F. So even though there's a kind of a nice thing that we can say about the upper box dimension, for lower box dimension there is no clean answer. In order to understand why there is no clean answer, we actually have to understand something a bit more difficult, which is get precise asymptotics for how does the covering number at scale R, like how does this vary as a function of R? And we'll get information about this question in terms of the number H, and in terms of this information about the set F. So this kind of thing is kind of morally similar to this problem, right? Like here we've obtained information about the upper box dimension in terms of H and some statistic in terms of F. And then now we're doing the same thing. We're obtaining some sort of statistic, some sort of covering statistic about lambda in terms of the Hausdorff dimension and a bunch of extra information. And then I guess the main thing that I want to prove, or the kind of the main kind of application, the main thing that can be said is the following. What is it? It turns out that there's actually so even though it's not possible to say to give a formula for the lower box dimension, it turns out that it's always possible to characterize when the lower and upper box dimensions coincide. So it turns out that the box dimension, so the lower box dimension of lambda is equal to the upper box dimension of lambda, if and only if one of the two things happens, either H, if and only if the maximum, I guess, what's the best way to, yeah. So the maximum of H and the lower box dimension of F is greater or equal to the upper box dimension of F. So even though there's no formula for the lower box dimension, we can still get a characterization of the existence of the box dimension only involving the upper box dimension, lower box dimension of H. So this is the plan for next time, in the self-similar case. So on Wednesday, the goal is to do this in the self-similar case, and then on Friday, talk about the self-informal case. What are all the extra hoops we have to jump through in order to deal with this like extra technical details? Okay, great.
Do we have any additional comments or questions?
So one little technical thing, the definition of F, I runs over alpha or what?
Sorry, this is over level 1, over the level 1 alphabet.
Level 1.
Exactly.
Okay. And I don't get why you said F is like almost same as 1 over B for D equals flat, because I believe that you are actually supposed to collect the fixed points of VB.
Yeah, so if you move each point in F by like a amount which is comparable to the contraction ratio of that thing, it doesn't change the dimension, it turns out. Yeah. I mean, so if you look in the notes, yeah, I mean this is not literally the fixed points. This is like
Not
yeah.
like say that it's like exact formulas more like
Okay, maybe let me draw this picture. Okay, this is a good point. Let's draw this picture. Okay. Okay, so we have a Gauss map. We have our branches, one branch like this. Okay, I'll only draw 3. Okay? So this is my, and then what are the fixed points? So the fixed points are along here. So this is a fixed point. So F, formally speaking, is like, okay, look at the branches that we retain, which is these branches, and we look at these. This is the point x of b.
yeah.
But what I'm saying is, well, instead of looking at x of b, this point is just like, look at the left integral instead. That's this set. Or maybe the right endpoint. Maybe it's the right endpoint.
Excuse me, I confused with your D versus Q. Sorry.
Ah.
Thank you. Yeah. Right.
Sorry. Yeah.
This
Yeah, there we go. Okay. Exactly. Yeah, so I'm sorry. This is, yeah. Cool. Yeah, so in general, if you have like a set which like intersects each of these images into like a single point or something, it will always be the same. But that's very believable.
This is well clear.
Okay, any other questions?
So in this setting, the attractor doesn't have to be compact.
Correct.
So if you consider closure of lambda instead of lambda, do you have formulas for Hausdorff dimension?
Maybe someone else knows
Can
this,
it
but
be
I suspect the
different
dimension will be the same.
Sorry?
The dimension should be the same. The Hausdorff dimension of the closure should be the same.
Okay.
Yeah.
Any additional questions? If not, let's thank the speaker again and